Okay, we continue. So, as I was saying, I've already expressed to you how you basically use the damage locating vectors. You apply them to the structure to look for regions of no stress. Now, the basic way, well, not the basic, the way that we compute the damage locating vectors is as the null space of the change in flexibility. So DLV vectors are the null space of the change in flexibility. Flexibility matrix. So let's clarify. First, there are, as far as terms, technical terms here, there is the issue of null space, and then there is the issue of flexibility, right? Now, for those in structural engineering, flexibility should be something that you're somewhat familiar with. Null space, perhaps not as much. I guess we might have mentioned it in the class or not, I don't remember. But I will clarify them right now. So, if we have a structure, right? We have a structure, any structure. And we define a model, which means we discretize. So now we have a model for the structure, right? Now, if I choose some coordinates, which are not necessarily all the coordinates of the model, right? The model may have a million coordinates, but I have these ones here. So this is coordinate number 1, this is coordinate number 2, this is coordinate number 3, this is coordinate number 4. In other words, the motion of that point in that direction, I call it 1, of this one in that direction is 2, this one in that direction is 3, this one in that direction is 4, and so on. So we say that Fij is a flexibility coefficient. If Fij is a flexibility coefficient, Fij is the deformation at I due to a unit load acting at J. Okay, so Fij is the deformation at I due to a unit load acting at J. So if I have those 4 coordinates, my flexibility matrix would be a 4 by 4, right? It doesn't matter that my structure had 1,000,000 degrees of freedom, right? It's defined in terms of the coordinates that I am selecting, which is going to relate to my sensors in a particular application that we're dealing with. But this is F11, F12, F13, F14, right? What is that row? Well, I go to coordinate deflection at 1 due to a load at 1. Deflection at 1 due to a load at 2. Deflection at 1 due to a load at 3. Deflection at 1 due to a load at 4, right? So I take this thing and I apply a unit load at 1 and I see how much 1 moves. That's F11. I put a unit load at 2 and I see how much 1 moves. That's F12. I put a unit load at 3 and I see how much 1 moves. That's F13. I put a unit load at 4, I see how much 1 moves. That's F14, right? It turns out that the flexibility matrix is symmetric. So F21, F31, and F41 are the same as their corresponding matrix, as their corresponding values of F12, F13, and F14. Okay? And likewise, the rest of the thing gets filled up. Now, DLV vectors are the null space of the change in flexibility. Now, the real question where system identification comes in, or the point in the stream of where the system identification comes in, is because the system identification is going to allow us to calculate the flexibility matrix of the structure without applying a unit load or a load at a certain coordinate, because in practice we just can't do that, right? We can't go in and say, let's apply a load on my building and see how much this thing moves. At best, we can put some vibrations. So the role of system ID is that it will allow us to calculate the flexibility matrix without having to apply the definition of apply a unit load at a position, right? But from the point of view of the DLV vectors don't care how you get the flexibility. We will get it with the system identification because that's the practical approach. Yet, the approach of the damage locating vectors could not care less how you get the flexibility. It just simply says the change in the flexibility before and after damage contains the information that I want. Okay? So now, let's zero in. Well, it's really raising poorly. Right? Okay, so I mentioned flexibility. I'm going to talk about null space subsequently. Let's just stick to flexibility for the time being. And let's do something very easy. Let's take this 3-story building, and let's say that the floor stiffnesses are equal to what? I mean, I could use realistic numbers like 100 or 500 or 1,000 or something like that, but then the calculation is going to get harder, right? So let's just use simple, small numbers so I don't have to stretch my brain when I'm computing things here. So let's just say that the stiffness of the first floor is 1, the stiffness of the second floor is 1, the stiffness of the third floor is 1/2. Okay? So let's say that that's our thing. We know right away how to calculate the stiffness matrix for that, right? More importantly, in order to talk about just the fact that I don't have to have all the points, let's just say that my coordinates are only these two. I don't have a sensor in the middle. I just have 1 and 2. So let's see what is the flexibility matrix for this case. So if we apply a unit load at the first coordinate, again, this is not the way that we calculate flexibility when we're going to do this problem in practice, right? We're going to extract the flexibility from the ABCs, right, that we get from ID. But they are exactly the same as this result that I'm talking about, so let's understand what it is. So if I apply a unit load at coordinate 1, the shear pattern is like this, 0, 0, and then 1 here, right? So the shear divided by the stiffness is the deformation, so that means that the first floor deforms 1, and the other floors stay like this, right? So if I push this with 1, the deformations would be this. The first floor will distort 1, the other floors don't distort, they just go for the right. So F11 is equal to 1. And F21 is equal to 1. Which is the same as F12. Right? Now, if we apply a load at the roof, which is the second coordinate, the shears through the floors are 1 everywhere, right? These are the shears everywhere, 1. No matter where you cut, it's 1, right? So, the deformation of the first level is 1, the shear is 1, divided by the story stiffness is 1. So the first level deforms 1, right? It's here at 1. The second level has a shear of 1 and a stiffness of 1, so it deforms 1 more. And so the second level goes like this, right? And deforms 1 more. The third level has a shear of 1 and the stiffness is a half, so it deforms 2 more, right? That means that that if I apply a unit load at 2, how big is the deformation at 2? If you said 2, that would be wrong, right? Because 2 is not the deformation. The deformation at 2 is this, which is 1, 2, 4, right? If you said 4, that would be correct. So notice that the deformation at 1 due to the load at 2 is 1, which is we already knew, and we put it here. So that is the flexibility matrix. Okay? For that case, from basic principles. Okay? Now, keep throwing this thing somewhere and I can never find it. Where is the dummy eraser that I'm using? Excuse me for a second. There it is. Okay, so I erase here. Okay, and that's the flexibility in the reference state, which in reality we're going to find, we don't know the model, we don't know anything, we're going to get it from the data using system ID, but we got it. Now let's say that we got damage, and the damage made this thing half. Again, I want to keep the numbers simple, right? So in the damaged state, only the first floor changed, and it was damaged, and now its stiffness is 0.5. You're going to say that's a lot of damage. Okay, it doesn't matter. It could have been 0.9, but if I make it 0.9, it's going to be harder to calculate the numbers, and it doesn't make any difference for showing the technique. So now we want to calculate the flexibility matrix again. So we take our structure, 1, 2, 3. We apply a unit load at 1, and we see that the shear pattern is this. Therefore, the deformation pattern is 1 divided by 0.5 is 2. And there's no shear in the other levels, so it's like this. Therefore, the flexibility matrix in the damaged state, F11 is 2. Okay? F11 is 2. And what is F21, which is this one? It's also 2, right? And we know that F12 is going to be the same, so this is 2. Now we have to apply the load on level 2. And so if we apply the load on level 2, here, unit load, the shear profile is 1 everywhere, right? The deformation profile is what? Shear is 1 in the first level and the stiffness was a half, so there is a 2 here. Shear on this level is 1 and this is 1, so that adds 1 more. And shear in this level was 1 and that was a half, so that is 2 more. And so we see that the deformation in the roof is 2, 3, 5, right? Therefore F22 is 5. I cannot overemphasize that this flexibility matrices in the reference state and in the damaged state must be computable without a model and without knowing where or how big the damage was, right? The fact that I am illustrating it with something that I know the damage and I know where it is just because that's the only way I can illustrate it, right? FR and FD will come out eyes closed to the model or the damage simply from the data. Now let's assume that we have. So I will erase here. and we will say, okay, we have the damage flexibility and we have the reference flexibility. Up to this moment in the process, there is no need to know anything about a model. There is all from the data. All we know is that we had two sensors because the flexibilities are 2 by 2. The DLV vectors are the null space of the change in flexibility. So that means that the first step we do is to calculate the change. And the change in the flexibility simply is the damage flexibility minus the undamaged flexibility. So 2 minus 1 is 1. 2 minus 1 is 1. 2 minus 1 is 1. And 5 minus 4 is 1. And so we see that the change in the flexibility, I don't know, yeah, I guess I need space. Maybe I need these things later, but I need space. So we have the change in the flexibility. So of my statements that the DLV vectors are the null space of the change in the flexibility, I've already showed you how you get what the flexibilities are and what the change is, which is just simply subtraction. Now, what is the null space of a matrix? When you, oh, good, I now remember that at the beginning of this class, we looked at the singular value decomposition with a little bit of time, right? So when you do the singular value decomposition of a matrix, there will be a set of singular values, right? The null space is related to singular values that are 0. Now, in our instance here in this presentation, I'm looking at a square matrix, right? Because it's number of sensors by number of sensors. The technique actually applies with non-square, but let's keep it square. So this thing will have a singular value decomposition that has, it's a 2 by 2 times a 2 by 2 times a 2 by 2, right? So the singular value decomposition of delta F will be a 2 by 2 times a 2 by 2 times a 2 by 2, right? And the singular values are these two, which will be S1 and S2. Now, it turns out you can see that these two columns are exactly the same. Therefore, this structure is really, this flexibility is rank 1. That means that one of the singular values, the second one, is actually exactly 0. If we write it as the product of three matrices and we put the last matrix transpose, then if there is 1, 0 here, that means that this is the null space. Actually, if I don't put the transpose, then it will be the last row. Okay? I put the transposes because when you say singular value decomposition in MATLAB, MATLAB actually gives you this times the transpose of the third matrix. So with the transpose, the null space is the number of columns that are associated with 0 singular values. If this was 3 by 3 and there were 2 singular values that were 0, then the last 2 columns would be the null space. Okay? If it was 10 by 10 and the last 3 columns, and there were 3 0 singular values, the last 3 columns would be the null space. What is the null space of a matrix? The null space of a matrix is simply this. If I have a matrix Q and I multiply it times L, and I get 0, then that is in the null space. Okay? The null space is not one vector, right? The null space is of some size. It could be one vector, like in this case, but it could be 2, it could be 3, it could be 4, it could be whatever, depending on how many 0 singular values there are. Well, maybe not whatever, because if it's 10 by 10 matrix, it cannot be 11. But it's some number, right? But any vector that multiplied times the matrix is 0, it's in the null space. Now, we can certainly calculate the null space by just going to MATLAB and doing the singular value decomposition if we want, right? And looking at the singular values and seeing which ones are 0, and boom, that's it, right? There is also a command null, but for reasons that I will explain later, it's better to think in terms of the singular values, right? Because if there is noise here, for example, this one was 1.002, then this would be rank 2. But when you look at the singular values, this would be 0.0003 or something. And you might say, okay, it's supposed to be really small, but it's just error, right? It's just noise. It's really meant to be 0. Although if you just say null in MATLAB, it'd say there is nothing, because there are no 0 singular values, right? So in this case, it's obvious that the rank of the matrix is 1. There's only one column of independent values. And the null space, I don't need to take a look. I can say by pure inspection that 1 and minus 1 is in the null space. Right? Because if we multiply times 1 and minus 1, we'll just get 0 and 0, right? So if we multiply the matrix times 1 and minus 1, we get 0, and that's the definition of null space, right? Now you could multiply times 2 and minus 2, or 10 and minus 10, it doesn't matter, because the null space are shapes, not values. So we conclude then that the null space of our changing flexibility is 1 and minus 1. And at this point, I believe we've gotten to the end, right? Have we gotten to the end? Yes, we've gotten to the end. Because we know that the DL vectors are the null space of the change in flexibility. We saw how we can get the flexibility, how we can take the change, and what the null space is. And so the DLV in this case is only one vector, and it's 1 and minus 1. Or 2 and minus 2, it doesn't matter. Now we go back to our structure, which was 3 stories, right? And it had a sensor here and a sensor here. And the DLV vector is 1 and minus 1, right? So that means 1 minus 1, right? Now, because it's a shear building, all that matters is the shear plot. So we start and we say, what is the shear on the roof? I mean, on the 3rd level, minus 1. And on the 2nd level, minus 1. And on the 1st level, 0. Now, if you remember, the damage was here, and we have identified that the damage is, in fact, in the 1st level, right? So, without the complications of how to obtain the flexibility, without the complications that in practice you may not be able to calculate the flexibility exactly because the identification has noise, without all the complications that always enter in practice, at least from a purely academic toy example, you can see the logic of the approach, right? I mean, at least the mechanics of the approach. The flexibilities are computed, the change is computed, the null space is computed, the null space applies at load, and boom, here's where the damage is located. Okay? So, with that in mind, I just remind you that in case I give you a homework that is not with a shear building, I remind you that the flexibility matrix is the inverse of the stiffness matrix. Now, that is the flexibility matrix if we have, imagine that we had this structure or do we, let me think if we need that or not. No, I was going to go along a complicated path, but let me not do that. If we had that structure that you can model with frame 2D, right? And if I wanted to know the flexibility, let me put another set of floors. Let's say I had sensors here and here and here, and I wanted to calculate the flexibility matrix. It would be a 3 by 3, 1, 2, and 3, right? If you model this frame as you know how to model with frame 2D, I don't think you've actually applied loads, but you can see by looking at it that applying loads is very simple. So one way to get the flexibility with frame 2D is you go here and you run this case. Apply a 1 kip at this level. And then you see the movement here, the movement here, the movement here, and those are your first 3 numbers. Then run the program again with the load here. You get this, this, and this, and then run with the program with the load there and you get this. So you can get frame 2D to calculate the flexibility matrix for things that are not shear buildings, and you can get the flexibility matrix for shear buildings by inspection, right? By simple understanding of what the definition is, and that's why we like shear buildings, right? Because we can do it without having to go to a code and do computations to calculate. So with this, I will leave for the next lecture the computation of how we obtain the flexibility matrix from the system ID. All right.